This is lesson 1.5, definition of the derivative. We're going to be verifying graphically and algebraically the rules for determining derivatives and apply these rules to determine the derivatives of polynomial functions. So by the end of this lesson, you should be able to determine the derivative to calculate the slope of the tangents to any point in a function's domain. This is a handy thing to be able to do because right now we've been looking at the instantaneous rate of change at one particular point. What this lesson is going to teach you is how to create the equation that's going to allow you to calculate that rate of change for any point along the curve or any point in a function's domain. There's some textbook questions for you to complete. The solutions from the textbook are posted already on the VLE. There's no exit ticket for today. Once you've completed the homework questions, you should be ready to go ahead and start the unit assignment that is already posted. We've already looked at finding the slope of tangents and how the function defining the tangent slope data gives the derivative of the original function and how we're able to graph that. And in this lesson, we're going to formalize those concepts, and I'm going to give you another equation. So let's take a look at this parent function and let's graph the derivative to this parent function. So this function has an equation of y equals x squared. It's a quadratic. So to find the points where the slope of the tangent is 0, we're going to look at where that slope is equal to 0, and that's going to be right there at that point. I'm going to put that point on the graph. Then we want to look at what's happening with the slope as it approaches that point from both sides. So if we take a look at what's happening from the left-hand side, we can see that the slope is decreasing and it is negative. So if we were to draw that slope of that tangent onto this graph, that is going to be down and to the left. Then we want to look at what the slope is doing as it's moving away from that point on the other side. That's going to be over here. The slope is increasing and it is positive, which means if we were to draw our tangent on here, it would also be increasing and positive. The equation of the original function is y equals x squared. The equation of the derivative will be linear. We can see that because it's a straight line, and it's going to be direct. It passes through the origin. So the slope of the tangent line, this y equals mx plus b, so this m value here is going to be the slope of the tangent anywhere along this graph, anywhere along this line. So if we want to find the slope of a graph, we're just going to use the slope triangle to figure that out. So I'm going to put this in a different color. So we go up to and over 1, up to and over 1, which means that my slope will be 2. So y equals 2x, and I don't have any b value. My b value is 0. So the equation for the derivative is y equals 2x. We know the derivative of a continuous function is itself a function. If it is a function, we should be able to get an equation, but which limit formula should we use? I apologize in advance. I'm not sure why when I'm saving these as PDFs, there's something weird happening. So I've just crossed out the incorrect function here, incorrect equation, and I've just rewritten it down here. So I apologize. I'm not sure why it's doing that. So we know that we can determine the slope using using the limits as 2 points get closer and closer together and that secant line approaches the slope of the tangent. And we can write that as the slope is equal to the limit as x approaches a of f of x minus f of a all over x minus a. But we can't use this if the 2 points are so close together that a actually equals x, because then we're going to find ourselves into a little bit of a problem. So I'm going to write it out for you. So the limit as x approaches x, which really is what's happening here, if a is getting closer and closer to x, it's becoming x, is f of x minus f of x all over x minus x. This doesn't work. All we're going to get is an undefined answer. So we can use the difference quotient though. So we can use the difference quotient as h approaches 0 because we can eliminate the denominator. So let's see what that looks like. So I have my slope is equal to the limit as h approaches 0 of f a plus h, that point that's just a little bit h distance away from the original point, minus f of a, all over that distance h. So my limit as h approaches 0. Now remember, we've got y equals x squared is our function, is our parent function. So this gives us x plus h squared minus x squared all over h. The limit as h approaches 0. So now remember, we've got to expand this out. We get x squared plus 2xh plus h squared minus x squared all over h. You'll see here that my x squareds cancel each other out. That leaves me with my limit as h approaches 0 of 2xh plus h squared all over h. Now we need to get rid of that h on the bottom, and to do that we're going to pull out a common factor. So the limit, and the common factor that we're going to pull out, remember, is h, because that's ultimately what we want to try and get rid of on the bottom here. So the limit as h approaches 0 is equal to h 2x plus h all over h. Now we have succeeded in eliminating that h from the bottom. We are left with the limit as h approaches 0 is equal to 2x plus h. Now we're going to substitute 0 wherever there's an h. So that tells me that this equals 2x. The equation of our derivative to the parent function of y equals x squared is equal to 2x. So here's our definition of a derivative. Recalling that the slope of a tangent at a particular point P with a and f of a is equal to the limit as h approaches 0, f a plus h minus f of a all over h, we can find the slope of the tangent at any point x. This derivative may be denoted by f with an apostrophe beside it, and this is pronounced f prime, where f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is called the definition of a derivative, or deriving a derivative. Let's put this in action and let's look at an example. Determine the slope of the tangent line to the curve y equals x cubed minus 2x squared plus 1 for any arbitrary value of x. So remember that our definition of derivative is telling me that f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to put that with our equations. We're going to sub x plus h into our equation of x cubed minus 2x squared plus 1 to help us calculate the slope of the tangent line. Okay, so we have f prime of x is equal to the limit as h approaches 0. And sad news is, yes, you should be writing that every single time. And that is equal to, so now I have my f of h, x plus h. So this is going to look like x plus h cubed from here minus 2x plus h squared from here plus 1 minus, now we just have our f of x, which is just the equation, minus x cubed, negative 1 times negative 2x gives me positive 2x squared, and plus 1 becomes minus 1, all over my value of h. This gives me my slope equation, or my derivative, of 3x squared minus 4x. And like I say, that's equal to the slope. So now we've accomplished determining the slope of the tangent line to a curve. This is our equation that we are now going to be able to use to determine the slope at any point along this particular curve. The next part of this question is asking us to determine the equation of the tangent line at 2 and 1. So we're going to determine the slope by solving f prime at 2. So just remember, sorry, I'm going to back up here for a second. Just remember that the tangent line is going to be a straight line. It's going to be linear. So it's going to be in the form of y equals mx plus b. So I need to know, for at a point 2 and 1, what is that equation going to look like? So I need my m value and I need my b value. So to solve for my m value, remember that m is equal to f prime of x. So f prime at 2. Now we're going to substitute 2 into our derivative. 3 times 2 squared minus 4 times 2 is going to equal 4. So we know now that the slope of this tangent line is going to be 4. I can now take this and sub this in to y equals mx plus b. So now I know that y equals 2x plus b. I also know that my y is 1 when x is 2. Sorry, y equals 4x plus b. So now I have 4 times 2 when x is 2 plus b. So I can solve for my b value. 1 equals 8 plus b. So my b value for my equation is negative 7. So now I can write my equation. Y equals 4x minus 7. That's the equation for my tangent line at that particular point, 2 and 1. So now the last part of this question is asking us to determine the points where the slope of the tangent is 0. So we want to know, where does m equal 0? So we are going to set our derivative equal to 0. So 0 is equal to 3x squared minus 4x. We're going to pull out a greatest common factor here, which is x. That leaves me with 3x minus 4. So I know that my two zeros will be when x equals 0 and when 3x minus 4 equals 0, or when x equals 3/4. So we will have 2 points where the slope is equal to 0. The slope of that tangent is equal to 0. That will be at when x equals 0, and it will be when x is equal to 3/4. An alternative notation for the derivative was introduced by Leibniz at the same time as Newton. He was around at the same time that Newton was inventing calculus. And he writes it as f prime of x is equal to dy over dx. Sorry, no prime there, I just was trying to show you dy over dx. So in the previous example, we would have d of x cubed minus 2x squared plus 1 all over dx, which actually does end up equaling 3x squared minus 4x. So let's look at an example. So let's say we have y equals x to the power of 4. Let's determine dy over dx. So dy over dx, remember, just an alternative way of saying f prime of x, or the derivative. So we're going to use the same equation, where it's f of x plus h minus f of x all over h. So our limit as h approaches 0 will be x plus h to the power of 4 minus x to the power of 4 all over h. Now, this is where doing this x plus h to the power of 4, Pascal's triangle is going to come in very handy. If you haven't taken a look at Pascal's triangle, I would suggest you go back and watch the video that I posted, or at a minimum, look at that slide from the lesson, because this will save you a lot of time when you're having to expand that. So the limit as h approaches 0 ends up equaling x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the power of 4, and then finally at the end we have this minus x to the power of 4, which came from here, all over h. So now we want to look for things that we can start to eliminate. So immediately I can see that this positive x to the power of 4 and this negative x to the power of 4 cancel each other out. And now I'm going to take an h out of every single one of my remaining terms in the top. So I'm going to cross that h out. That gets rid of that. This becomes h, just h. This becomes h squared. And this becomes h to the power of 3. The only term that's left in this whole thing that doesn't have an h in it, so when I go and substitute 0 for all of the h's, the only one that doesn't have an h in it is this 4x cubed. And that, my friends, is the equation for the derivative, 4x cubed. So my dy over dx, or my equation for my slope of my derivative, is 4x cubed. Let's look at one more example. The derivative of a function is shown below. So here we have the derivative of the function. The limit as h approaches 0 is 2 plus h squared minus 4 all over h. And we're being asked to determine the function, the point, and the slope of the tangent line. So all that we're going to do here is just reverse the process that we did previously. So what we know that f prime of x is equal to f of a plus h minus f of a all over h. So if that's the case, then my original function, f of x, must be x squared. I know that because I'm looking at the fact that 2 plus h is squared. So f at 2 is equal to 2 squared, which is equal to 4. So here's our equation. Now we're going to find the point. So we know our x value is 2. Again, from this original equation. And that gives us a y value of 4. So our point is 2, 4. And the last part of this says determine the slope of the tangent line. So now I'm going to use my f prime of x, which is equal to 2x, to determine that f prime of 2 is equal to 2 times 2, and my slope equals 4. So again, we just reversed the process and used what was in the derivative of the function to figure out the original function, the point, and the slope. Okay, that's it for this one, and that's actually the last lesson for this unit. So there's some homework questions on page 58, and once you're done those, there's no exit ticket today, but you can go ahead and start the Unit 1 assignment.